For our next coordinate system, we extend the 2D polar coordinate system into the cylindrical coordinate system. The cylindrical coordinate system takes the 2D polar coordinates and adds on the z-axis. As a result, it is natural to think that the coordinates should be called r, phi, and z. However, there are a couple of problems using r as the name of this coordinate. For one, it could be confused with the r from spherical coordinates, and the other reason is that if we use r, then we have a problem because the magnitude of the position vector would not be equal to that. So we need a new name for this variable, and so traditionally the letter used is the Greek letter rho. So we have rho, phi, and z. However, even this is not completely standard. You will find, for example, Griffith's textbook uses the letter s instead for this coordinate. But in this video we will use rho, phi, and z. So with that in mind, what is the actual expression for the position vector? Well, if I want to get to this point, then I need to move out some distance rho and then move up some distance z. So the r vector becomes rho times rho hat plus z times z hat. And this is the position vector of the point. A lot of the same relations from 2D polar coordinates carry over. So for example, we have x equals rho cosine phi, y equals rho sine phi, and well, z is just equal to z. If we want to go the other way, we have rho is equal to the square root of x squared plus y squared, phi is equal to arctan y over x, whoops, and well, z is still just equal to z. We can still follow the same rules as before to get expressions for rho hat in terms of x hat, y hat, and z hat, but I will leave that as an exercise for you. So with that in mind, what else do we have to look at? Well, we've seen what the position vector is. The infinitesimal change in position vector is d rho rho hat plus dz z hat, and then of course, even though z is constant direction, rho is not, so we would have rho times, sorry, rho hat is not constant in direction, so we'd have rho times d rho hat. But just as before, in 2D polar coordinates, we can substitute for d of rho hat, and d of rho hat is equal to d phi times phi hat. So our final infinitesimal line element is dr vector is equal to d rho times rho hat plus rho d phi times phi hat plus dz times z hat. A few points to note. One is that this order of rho, phi, and z is important because it is in this order that they form a right-handed coordinate system. So in other words, rho hat cross product with phi hat equals z hat, phi hat cross product with z hat equals rho hat, and z hat cross product with rho hat equals phi hat. the way I remember this is I write rho phi z, rho phi z. So then rho hat times phi hat is z hat, phi hat times z hat is rho hat, z hat cross rho hat is phi hat, and if I go in the reverse order, phi hat cross rho hat, that's minus z hat. Rho hat cross z hat is minus phi hat. We might also be interested in area elements. In this 3D coordinate system, there are 3 easy surfaces we could work with. We could look at surfaces of constant rho. So if we hold rho constant, then we trace out a circle and extend it in the z direction, so it's a cylindrical surface. And our dA would come from, we're holding rho constant, so this goes away and we take the cross product of these two. So we have rho d phi dz, and then phi cross z hat ends up being phi cross z hat is rho hat. Similarly, we could have a surface of constant z. Constant z means we'll have a planar surface holding z constant, and our dA, so since z is constant, dz goes away, we take the cross product of these two, and our dA would be rho d phi d rho, and we have rho hat cross phi hat, which is z hat. Finally, we could hold phi constant. So first, as a reminder, dr vector is d rho rho hat plus rho d phi phi hat plus dz z hat. So if we hold phi constant, then this term disappears. The surface would again look like a plane, but it would be, so we have the circles, we're fixing our angle phi, so we have a plane that extends in the rho and z directions out from the origin. This is the rho direction, this is the z direction. So dA with phi constant is equal to cross product of these two, so we have d rho dz, and then we can do, well, depending upon which way we want it pointing. Let's say we want rho cross with z, then that points in the negative phi hat direction, or you can have z crossed with rho, and that would point in the positive phi hat direction. So let's go with that for the moment. All right, and then the volume element would be simply the product of all 3 of these factors. So we would have rho d phi d rho dz. And then the other common 3-dimensional coordinate system, the spherical coordinates. And these are denoted as r, theta, and phi. Unfortunately, occasionally mathematicians and physicists follow different conventions about which angle is theta and which angle is phi. However, all physicists follow the convention that the idea is that the phi is the same from the 2D polar coordinates. It's the angle in the equatorial plane, whereas theta is the angle from the North Pole axis. So this would be theta. This type of angle would be phi. And of course, r increases radially outward from the center. So r vector in this case is again just r hat. Now r hat is a function of both theta and phi. The coordinates are related to x, y, and z. We have x is equal to r cos phi sine theta, y is equal to r sine phi sine theta, and z is equal to r cosine theta. If we want to go the other way, we have r is the square root of x squared plus y squared plus z squared. Phi is equal to arctan of y over x, because we can see the r's would cancel out, the sine thetas would cancel out, and we just end up with tan phi for y over x, and so arctan of that. And then theta is equal to the arctan of square root x squared plus y squared over z, because we can see that x squared plus y squared would give us r squared sine squared theta, square root that, so r sine theta divided by r cosine theta leaves us with tan theta, so arctan of that gives us theta. The right hand coordinate system is r theta phi in that order. As usual, r hat cross theta hat will give us phi hat, theta hat cross phi hat will give us r hat, phi hat cross r hat will give us theta hat, and so on. dr vector will now be a little bit more complex because r hat is a function of both theta and phi, and in the end what we get is dr r hat plus r times dr hat, which ends up being dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. Again, there are three possible easy surfaces that we can consider. There is the surface of constant r. So for constant r, dr would be 0, and we take the cross product of these two, and we get dA is r squared sine theta d theta d phi r hat, and this would be the surface of a sphere, and we have the normal vector pointing outward. For constant theta, we can see that constant theta would actually describe a cone, and here we would have dA is equal to dr times r sine theta d phi, and when we have phi hat cross r hat, which would be theta hat. And then finally we have constant phi. For constant phi, we would have a plane in the r theta direction. Well, since theta varies from 0 to pi, it would be more of a half plane extending out to infinity. And so we would have r dr d theta phi hat. And then finally we have the volume element, which is r squared sine theta dr d theta d phi.